introduction. I will give about 2-minute introduction.
There you go. Sure. No problem.
We'll start, right?
We'll make it work across. We have 2 games.
It's a digital clock right there.
Okay, I think it's about a time. It may be a little unusual to introduce a speaker about talking about myself. Let me tell you something about myself. I graduated in, I was getting my master's in 1970, 71. And at the time, as a student, one is always looking for something new. And a new thing at the time suddenly showed up in the form of digital signal processing. And I was struggling with this. I was back in what used to be Czechoslovakia, behind the Iron Curtain. I was struggling with this copy of the book, which I have no idea where it came from. It was all on a blueprint, mimeographed, and authors were Gold and Rader from Lincoln Laboratories. And we were truly worried, like, how is it possible that you can do filtering without any capacitors and coils and anything, because I was, of course, trained as an analog engineer. And when I came to this country and I met Ben Gold, I told him about that, and he told me that he was actually struggling with the same thing, except a little bit earlier than I was. So we started talking about it, and I realized that it's a really fascinating story, how the new field, such as digital signal processing, can be born seemingly from nowhere, only because the certain knowledge is there, certain desire is there, and certain people have a certain problem. And so I asked Ben to come and tell us about all that. And Ben was kind enough that he prepared a full talk, which he will give today. Ben, please.
Thank you, Heini. Can everybody hear me? Good. Well, this is a personal early DSP history. And what I've listed here are sort of the course of events that I followed personally, which finally led me to eventually write a book and start work at Lincoln Lab on DSP hardware, which takes us to about 1970. So the history really goes from, I'd say, 1955 to 1970. And I'll try to sort of go over it quite rapidly. I'll probably be referring to this over and over again, but let me put it over here and just start talking about these personal reminiscences. I came to Lincoln Lab. It's an MIT lab, as most of you know. In 1953. I did some work on statistics for Bill Davenport, and then I got a Fulbright fellowship and left in 1954 to spend a year in Rome, Italy, which was great, and came back in 55, and things had changed. There was a new boss. His name was Oliver Selfridge. And a new subject, to me at least a new subject, and also fairly new, called pattern recognition, which eventually led to the artificial intelligence field. So I had to do some work. Oliver suggested that I work on something called a Morse code translator. The idea was, it's a pattern recognition problem, hand-sent Morse code was the input, and the machine that I was supposed to build was to produce English text from that input. So we worked on that for a while. And in the process of working on it, I used to hang around with Oliver a lot, and he introduced me to another concept, which, by the way, I did not use in the Morse code translator. He talked about the concept. He was a very esoteric type of person. He called the concept pandemonium. And by pandemonium, he really meant parallel processing, it turned out. The idea is that you have, in the human brain, you have all these neurons, and they're all going about doing their own business, and each different neurons are doing different things, and so what you have really is pandemonium. All these millions of neurons doing different things, and out of it comes a result, somehow. Like you you say a word, or you recognize a face, or you see your car, or whatever, all resulting from pandemonium, which is parallel processing. It's a fascinating idea. Anyway, Oliver was and I was in that group, he was the boss of the group called Pattern Recognition Group at Lincoln Lab. And management didn't like it too much, it turned out. So what they did was they took first 4 good engineers from that group, I was one of them, and moved the 4 of us to a different group. And then a year later, they disbanded the pattern recognition group completely. So I guess the idea was, well, these 4 guys are okay, so we'll move them where they can do some useful work, and we'll get rid of the other guys. We'll get rid of Selfridge, we'll get rid of Alan Tritter, we'll get rid of, actually, some people you might have heard of. Marvin Minsky was one of them. He was told, look, work on what we like or leave. So he left and did AI, and we all know about that. Anyway, I guess the management isn't always very prescient. There'll be a few other examples like that. So I'll be, by the way, rambling a lot along these lines, and you can stop me. You can stop me at any time and ask any question you like, of any sort, about anything. Who was the management? Well, I'm not sure. Actually, it was Bill Davenport, the fellow who hired me. Right? He was a communicator. The other interest, actually, there was an interesting side thing on that. Bill Davenport's brother-in-law was Jerry Deneen. I don't know if you've heard of him, but he actually was a Lincoln Laboratory director for a while. And Deneen did not get along very well with Oliver. So maybe that's part of the problem. Anyway. So this is a funny kind of talk. I never give talks like this. I give talks like, you know, you show you the VU graph and you point to it. And so this is a little different. And you'll have to bear with me. Anyway, I was now in a different group. I was in a group that, not quite sure what the group was about, to tell you the truth. In fact, when I got into that group, I didn't quite know what they were about. I knew that the boss of the group was a fellow named Paul Rosen, and he didn't tell me anything. He just said, well, you're in my group. I don't care. I mean, he didn't really say it, but basically it amounted to do whatever you feel like. And in those days at Lincoln Lab, that wasn't too unusual. So I looked around, and what I found was a fellow named Jim Forgey, who was working on speech recognition. This is in the late 1950s now, and on a computer called TX2. There's a part of the computer. This gentleman here is Omar Wheeler, who's now gone, unfortunately. A lot of these people that I'll be talking about are gone. And he didn't design the computer. He actually knew how to fix it, which is a very, very important thing. But if you look here, I guess I could, oh, thank you. That's very useful. Yeah. What you see are a bunch of switches. And these were actually registers that you could change, and they were part of the computer memory. So while the computer was running, you could actually move these switches up and down and change things, and it turned out to be very useful. Anyway, I don't want to dwell on this. This was a computer which, for that day and age, and this was in the 1950s, had 64K of memory, which was considered enormous. And, you know, it was a powerful thing. The inventor of core memory actually was Jay Forrester, and he was also at Lincoln Lab and helped design this computer, although he didn't do much in the way of design. He did more in the way of administration. But he did invent the core memory, which was the basis of this 64K memory. The other thing about that computer that was great was it had a very, very flexible input-output system, which I'll talk about more later. Here's another picture of TX2, just sort of the rest of it. Stuff in here. In other words, the computer took up the whole room, basically. It was a big computer and very, very powerful for its time. And the way that Jim Forgey did speech recognition, I mean, I don't want to get into the algorithms or anything like that, but just the methods he used. He used a TX2 computer, and he had a large 36-channel analog filter bank, which was multiplexed. Its output was it was a filter, a bunch of bandpass filters, followed by rectifiers and low-pass filters. And the low-pass filters now were at a reasonable size. No, is it? No, I don't like it. You couldn't hear me before? Oh, okay. Actually, it is better. Yeah, good. I'm used to it by now. Can you still hear me? Okay. You couldn't hear me before? I'm really sorry. You should have said something. Okay. So where was I? I was talking about the... oh yeah, Jim Forgey, right, yeah. Yeah, he had this filter bank that he was able to read the outputs of the filter bank, not the bandpass output, but the low-pass outputs, the amplitudes of these at different spectral points. He could read the spectrum based on the filter bank into the computer, and he used that to do speech recognition. And we won't talk about the actual recognition algorithms. he actually, one of his rather innovative early programs was to do the, if anyone's heard this, the bit, bat, butt problem. In other words, he took 10 words: beat, bit, bat, butt, bought, bird, and so on, and recognized one of these 10. So that's similar to some of the problems we're still working on, right? You know, the digit problem.
It's about the same idea. I
Yeah,
think.
and he got pretty good results. Anyway, so why am I even telling you all this? Well, I got it at that time. When I first came to work, I didn't know what a computer was, really. 1953, they existed, and in fact, Lincoln Lab had a computer, but most of the people didn't know what they were or how to use them, and I certainly didn't. And it wasn't until I came back from Rome, and this is now 1955, and started working on this Morse decoder, that I looked around and there were certain people working there who were called programmers. And a programmer was supposed to take your ideas and turn them into something that ran on a computer. So at a certain point, I started feeling that I better learn something about it. So I went to an IBM school and took a class, 3-week class. This was like 1958. I said, oh, that's what a computer is. It's trivial. I mean, it actually, I mean, once you take a class, you realize a computer really is a very, very simple thing. So then when I discovered Forgy and TX2, I said, well, maybe I can do something with a computer that's interesting. And the problem that came to me, and I really don't know why exactly, I got interested in vocoders, and I got interested in pitch detection, and I started feeling that maybe I could do something interesting. And as I pointed out, when we were transferred away from Oliver Selfridge's group, we sort of had this carte blanche. Nobody told us anything. Maybe they thought we should just go away and quit. But we didn't do that, and so we could do anything we liked. So here's what I did. I went to Bell Labs. I mean, as a visitor. I didn't just quit and go to Bell Labs. And I spoke to 2 people. I spoke to Ed David and John Kelly. Now, Ed David was the boss of the sort of the speech and vision group, and John Kelly was doing some programming. And what he told me was he told me 2 things. First, he says, vocoders are very interesting. Secondly, he said, the hard problem with vocoders is pitch detection. It's easy to build a filter bank, but it's hard to detect pitch. That's a pattern recognition problem. So what I came away with was, number 1, hey, maybe I could do something on TX2. Number 2, I don't think pitch detection is that hard. I think I can do something. So let's see, what else? Yeah. And number 3, if I did pitch detection, maybe we can then build vocoders, because vocoders are interesting. So I came back to Lincoln after this trip and wrote a program on pitch detection. It took a while, but I did it. And now the question was, how do you, okay, so here's this computer, TX2, here's my program. What do I do now? I don't have a vocoder. Okay, well, here's the way we figured out what to do. The computer was able to produce pitch. In other words, it computed pitch. The computer also contained the speech. So it wasn't too difficult, given the flexibility of TX2, to produce a 2-track tape which contained on one track the speech and the other track the result of the computer pitch. We took this tape to Bell Labs. They had a vocoder. We didn't. And we actually were able to play both the speech into the channel part of the vocoder, that is all the filter bank, and play the pitch into the excitation part of the vocoder. So we did that and produced a version of vocoded speech using our pitch detector. Took that back to Lincoln and played it for people. And said, see, look how good it is. It was pretty good, actually. So anyway, that was, why am I even telling you all this? Well, I'm actually leading up to digital signal processing, believe it or not. I hope I am, anyway. Well, Paul Rosen was, as I say, the boss at that time, and he heard the tape, and he said, hey, that's pretty good. Maybe we should build our own vocoder. So, okay, now there was a little glitch that took place. Here, let me try to explain this. This is something like the vocoder synthesizers that we use at Bell Labs. Ignore this and just think of this as the entire filter bank, the entire synthesizer filter bank, which in this case had a bank of limiters and another filter bank, and then a bank of modulators which came from the analyzer, which you don't see here, and finally the speech output. So that was the experiment that I just talked about. And presumably that's what we should have built. We should have built this plus the analyzer, which is also a filter bank. But Paul Rosen didn't let us do that. He said, look, it looks too expensive. There are two banks, there are two filter banks. One filter bank should be enough. What he said was, why don't you, thank you, build something like this, where this is your excitation signal from your pitch detector, and I'll build you up a filter bank with modulators, and that should be okay, right? Well, I don't want to get into great detail, but it wasn't. It wasn't too good. And what we eventually had to do was build the original filter bank, similar to the one that we tried out at Bell Labs, in order to get good quality speech. So now we had gotten to the point where we had a whole vocoder, and it was good. Well, we didn't have a whole. What was missing? The pitch detector was on the computer. We had an analog filter bank. We had actually a bank of, there were actually 3 filter banks, one for the analyzer, 2 for the synthesizer. And then there was the pitch detector, my pitch program. So, okay, I've done all these. Yeah. At that point, the boss said, why don't we build a whole vocoder, including a hardware version of your pitch program, as well as the filter banks that are needed. So they took a look at it, and in fact, this I think is an interesting aside. Paul got together with his hardware guru, who was really a great hardware guy, Norm Daggett. And they looked at my design. How am I doing, by the way? Okay, yeah. And they said, if we try to build Gold's algorithm in hardware, it's the biggest kludge you ever saw. That they said, we don't want to build anything like this. It's very awkward in hardware. It's great on a computer, but it's a terrible piece of, it would be a terrible piece of hardware. So they suggested to me that I go back to the computer and completely redesign the pitch program, which I did. And it came out much, much better than the original. So the lesson is, if you build something, not only should it be effective and good, it's got to be beautiful as well. And this is my beautiful pitch program. It's very, very simple. It uses 6 elementary pitch detectors, and then it takes all of those and makes sort of a complicated statistical type of computation. And it turned out that this was a good pitch detector, and they did build this, and we had a vocoder. And so that's the end of story number 1. How far did I get? I got up to here. Okay, and I haven't said anything about DSP as yet, but now I will. Any questions at this point? No questions. Okay. So we had a vocoder. What do we need DSP? We had a pitch computer. We had 3 banks of filters, all the necessary rectification, everything you liked. Okay, so people would say, do you really have the best filter bank? How many filters do you use in a filter bank? Is it 10? Is it 20? Is it 30? Is it 40? What's the right number? What should be the bandwidths of each filter in the filter bank? You do something, but I think what we did originally was make uniform bandwidths. What about the design of the filters? Should they be Butterworth or Chebyshev or elliptic? I mean, there are a million options. Well, all this led us to feel that wouldn't it be great if you could just put all these filters in a program and try them out that way, so you wouldn't have to build each one separately. And I think that was probably the most important motivation for us guys, people who are interested in vocoders and speech, to get interested in digital signal processing. Now, we had heard, for example, that Max Matthews had programmed a vocoder on the computer that took like 3 hours of running time per 1 second of speech input. And I think his main point was, hey, look, don't try to do it, because you'll spend the rest of your life trying to find out any information with that kind of running time. Meanwhile, we had heard, or we had actually met Jim Kaiser, who was talking about doing digital filtering. So we got really interested, and by the way, this was our vocoder, nice big device. Okay. And I think, I'm not sure whether this was before the pitch detector was built, but if the pitch detector was in it, it was took up something like that, and the rest of it was all filter bank. So that was a problem at that time. Anyway, Charlie Rader and I decided, if this digital filter thing really makes sense, let's see if we can understand it. And the key, it turned out, in my case, to understanding it, was this book, which had been laying in my office since probably 1950, like for 7 or 8 years. And there was a chapter in it that I had never read, which was called Filters and Servo Systems with Pulse Data. And it turns out, if you read the chapter, that this gives you the exact theory of impulse invariant high IR filters. So it was all there in 1948. But it was used entirely for control theory. Nobody seemed to be interested in designing Butterworth, Chebyshev, and elliptic filters. And we now felt that information plus the work that Jim Kaiser was doing at Bell Labs, plus another very important input. Where is it? Here. From a guy named, who I don't know if anybody really knows him, a guy named Joe Levin, who at that time was working at Lincoln, was actually teaching a course on sample data systems, again, oriented towards control. But when we spoke with him, he picked up the new ideas very quickly, and he suggested that the three of us really work on it together, which meant mainly listening to him because he knew a lot about it and we didn't. And so I think between Harevich, who wrote the book, who wrote the chapter in the book, and Joe Levin, Charlie and I learned all about digital filters, or learned a lot about them. Learned enough about digital filters to start doing work, basically. And that was really the basic, well, that was one of the basic things. There was another pretty important thing. A fellow named Ben Logan at Bell who we had never met, by the way, and we still haven't met him, presumably had programmed a filter using this concept, which I later called frequency sampling filters. And it's as you could see, it's a delay line and a resonator, and resonators. And here are a bunch of resonators, one delay line, really a comb filter, and then a bunch of outputs like this. Now, I don't want to go into this, but as I say, it's, I think a lot of people give me credit for talking about it. I did invent the name, but I think the original basic idea came out of Ben Logan. Well, before I go any further, I want to just point out sort of one of these tragic things that take place. Both Horevich, who had written this chapter, and Joe Levin got killed just around that time, just in the early 1960s. Horevich fell off a mountain, actually, and got killed. And Joe Levin was driving on the Mass Turnpike, and somebody on the other side jumped the line. So there was some accident, and he crashed right into him and killed him. So we were going to, the three of us were going to write this digital filter paper, because by now we knew how to design filters, and we had programmed it, and we knew about quantization effects. We knew about FIR and IIR, although we hadn't used that name yet. Non-recursive and recursive was what we said. And so Charlie and I decided we'll write the paper. We did, got published, and it was a good, solid paper. I think it came out about 1964 or something like that. And it was sort of the theory and design of digital filters. So we were well on our way, but the story isn't complete yet. Let's see how far we've gotten. Basically got up to this bullet over here. We were now sort of in the, we now had vocoders on the computer. Instead of taking 3 hours per second, it only took a couple of minutes per second. Yes?
How good was your data acquisition system? Like, how high sampling rates could you achieve? Like, you could sample speech fast enough, or could you sample music?
We tended to use, we were mainly interested in telephone speech at the time, interested in 4 kilohertz speech. And we sort of just decided on 10 kilohertz. But it wasn't necessary. We could have used 20, but that would take twice as long. And I guess we could have used lower, but lower seemed not good enough. So 10 was sort of the standard rate. When LPC came along, we switched to 8. Again, just to save time. It wasn't only us. By then, everybody was involved. But 8 seemed to be a more popular thing. Okay. Yeah.
At the time, 10 kilohertz sampling, wasn't that very high for those days?
Was high?
Yeah, for those
For A
days.
to D?
You mean for?
A to D, yeah.
Well, no, there were A to Ds that did that. And then the question is, what was the, what kind of quantization did they have? I believe, I don't remember exactly, but I believe that we were using it then 10 kilohertz and maybe 8 to 10 bits. I think we were able to do that. And we're talking like the mid-1960s now. Pardon?
They already had communication circuits that would be fast enough.
Yeah, I think so. Yeah, anyway, we had it. I don't know who else had it. Okay, the next water. I'd like to point out, by the way, that while all this was going on, we were still thinking of ourselves as vocoder people. We weren't saying, hey, we're digital signal processors or anything like that. We're just doing vocoders, and here's a nice technique to use. You know, programming vocoders on a computer is really great, but basically just to try to get a better vocoder. And we weren't yet thinking that digital signal processing as a thing was, you know, really a great new thing that was coming out. We were just vocoder people. Anyway, in fact, at that point, I started thinking that maybe we could write a book on vocoders. I spoke to Charlie about it. He was interested. And I started doing some writing. And as I kept writing, I found that a lot of my writings went into digital filters for some reason. But then at that point, something interesting happened to me. It was just luck. Ken Stevens called me up one day. He was the speech guy at MIT. And he said, how about spending a year on faculty at MIT? And it seemed to me like a nice thing to do. It was also, I wasn't going to lose any money doing it, which is important. And it was sort of different that I'd have a chance to do some teaching. Well, it turned out that, anyway, I did it, I accepted it, and I wound up teaching what probably, well, certainly in New England, the first DSP course, and it really wasn't a complete DSP course because the FFT hadn't been invented yet. So it was a digital filter course mainly. It had the FIR filters and the IIR filters and a lot of issues of, you know, about filter networks and quantization effects, but the FFT hadn't really come along yet. In fact, it came along towards the end of 1965, and the way I heard about it was through a fellow named Tom Crystal, who was my teaching assistant in that course, who went to Bell Labs as a student, a summer student, and who one day came back with a report by two gentlemen named Cooley and Tukey. He said he didn't understand it, and he said maybe I could. So I looked at it, and I didn't understand it either, but the first paragraph blew my mind because it had this n log n thing. I said, oh my God, this is fantastic. But I don't understand how they did it. So I gave the paper to Charlie, and he and Tom Stockham figured it out. And they came up with these flow charts, and then I understood it. The flow charts really made sense. Although Jim Cooley says he never could understand flow charts, he could only understand triple sums. And so, you know, everyone's different. But anyway, the flow charts really, I mean, everybody knows flow charts. I don't have to show them to you. These are right out of the book that Charlie and I wrote. I'll sort of skip them. Actually, there's one very nice one. This is, notice how it's so different looking than the other one. But it's pardon? Not really. There's no very structured stuff. No pandemonium here. The only pandemonium, now where did pandemonium come? I think I forgot to mention it, that it was back when I did the pitch detector, because what I did was parallel processing, which is another word for pandemonium. Now, a lot happened from that course, and I think that's what kind of really got things really moving very heavily. First of all, Larry Rubino was in that course. He was a student. And anybody who knows Larry knows that things move when he gets involved. And he did. He got very, very interested right away and started using it. The other thing that happened was Al Oppenheim heard about the course. He didn't take it. He was a young faculty member at the time. And Bill Davenport, I think, told him about me. So I met Al, and he got also very interested. And I think we know what happened there. One of his early students was Ron Schaefer. And so between Oppenheim, Schaefer, Rabiner, and me, we really had the field going very strongly. And I think we wound up writing these big books that sold a lot of copies, which was really nice. So, okay, so that's the that gets us up to here. And now there are just two things left. One is what is called the capture of either the IEEE or the IRE transactions on audio and electroacoustics. That was a transactions that was slowly dying over the years. Somehow nobody seemed to be interested in it. And it got thinner and thinner and fewer people. And so we, for some reason, we decided maybe we can capture it and make it get more popular. And that's exactly what happened. And the thing that triggered it off was a conference that was sponsored at the Air Force Laboratory. Lincoln Lab is on an Air Force base, if you guys don't know that. It's the Hanscom Air Force Base. And for a long time, they had some speech efforts. One of the gentlemen that was heavily involved in speech is a fellow named Caldwell Smith, Caldwell P. Smith. I think he must be this one here, because I know the other three. This is Gunnar Font, this is John Pierce, and this is Bill Lang, and this is Homer Dudley. And what they did was they had this conference, and as part of the conference, they gave a big award to Homer Dudley. He had just recently retired from Bell Labs. And in fact, here's a picture of John Pierce, who is now also retired, of course, and working at Karma at Stanford, giving this award. It's sort of called a Society Award to Homer, who, by the way, consulted with us for a few years after he retired.
This was in 69, 68.
Pardon?
What year was that? About 68?
I'm guessing that this award was like 1968, 69, something like that. Yeah, that's what yeah, it's around then. And in fact, that Charlie and I wrote this big digital filter paper, and we published it in the proceedings of the IRE or IEEE. I don't know when the change took place. So that was fine, but you can't use the proceedings as a standard sounding board for papers. You need a transactions, and we didn't have any. So how do you publish papers? And the answer was we captured the transactions on audio and electroacoustics, and that started getting fatter and fatter, and became one of the most lucrative of all magazines. And finally, we wound up changing the name because it really wasn't audio and electroacoustics anymore. It was acoustic, speech, and signal processing. And that's still exists now.
Now it is back. Now it's speech and audio split off.
I know, it got so big that it started splitting off. And now there's something called signal processing, which they never had at that time, by the way. Signal processing was not a big deal. So now we're just about done with the decade. And the final thing that I just want to say is that it seemed, and I don't think I was the only one who thought of this, but I was one of them, said, hey, why don't we build computers that are oriented towards digital signal processing? And my boss liked the idea, so we built this monster. This is called the Fast Digital Processor. And these two cabinets actually are filled with hardware. And it was a machine that could do an FFT and digital filter very fast. In fact, I believe the first, around that time, LPC came out. I'm not going to get involved in that because that's already more modern times. I'm talking about ancient history. But this machine actually did the first real-time LPC, as far as I know. Ed Hofstadter wrote the program. And finally, we built something. Technology was moving along at this great rate, and we built what we call the Lincoln Digital Signal Processor, which is really these two boards. This is just a power supply. And we used that throughout the 1970s to do digital signal processing. And I think at this point, I'm ready to stop. I hope you have questions.
I have one question for the record. Did Tom Crystal understand FFT or didn't he understand FFT?
At the time?
At the time.
At the time that he gave me the Cooley-Tukey paper?
Yes.
He certainly did not,
Did not,
but
okay.
I did not either. Yeah. Nobody did. The only person, well, Cooley understood it. Tukey may have. And did you ever hear the story about how that happened? Tukey, I forget who told the story. It was some IBM guy, Richard somebody, who was sitting at a conference with Tukey. And Tukey was doodling, and this guy asked him what he's doing, and he told him something about FFT, which, by the way, Don Johnson showed that Gauss had actually invented the FFT, right? But we'll ignore that for the moment. In modern times, Tukey is the guy that deserves a lot of credit. But this IBM guy actually took the idea over to Jim Cooley and said, could you write a program? And Cooley wrote a program. So he understood it. Charlie Rader, after reading the paper, really understood it, and really understood maybe better than anybody. And after a while, even I got to understand it and wrote programs. Tom Stockham did high-speed convolution based on the FFT. Tom Crystal, no, he was just a student at the time. He didn't understand any of that stuff. More questions?
So when you were talking about the very early vocoders, when you were putting stuff onto 2-track tape, what was the actual format? How did the data get represented to the computer?
Well, you start out, you have an A to D converter, and you have the computer. So you could read the speech into the computer. Okay. Now I have a program which actually computes pitch and then marks. I mean, let's say you have his memory. Okay. All the program has to do is mark pitch pulses at the appropriate places in memory. And it does that in one way or the other. I think in TX2, all you did was flip it. There was a bit which said, there's a pulse now. Then the next issue is how do you read all this out? And it turned out with TX2's flexibility, you actually had two separate outputs. One was the speech output, so you could re-record the speech that you had sent in, and at the same time, you can send out those bits that were lined up with the speech and just make a two-track analog recording. And so what you had on one track was a speech, on the other track was the pitch in sync with the correct, with presumably the computed pitch. Whether it was correct or not, I don't know, but the computed pitch. And then you simply have to feed that into a regular analog vocoder, which we found at Bell Labs. Yes?
I was wondering, statistical time sequence or time series analysis was a topic that was already worked on at that time, well, wasn't it? It came afterwards? Or?
It was time series? No.
Yeah, time series analysis. Why was it such a big jump to go to
digital
signal processing?
Yeah, as a matter of fact, I don't know. I mean, but you know, there was another thing. In radar, there was something called the Butler matrix, which is really a hardware FFT. So, and I think a fellow named Good had also done work about 10 years ago, which, if you looked at it carefully, did something like an FFT. So it was sort of around, but I think until Cooley and Tukey and then Charlie Rader, I think Rader actually deserves a lot of credit because of the flowcharts. Until they put that act together, it really didn't excite anybody, and all of a sudden everybody got very excited, rightfully so. You know. Yes.
I was going to say that, not in the FFT, but some of the work on the autoregressive filters or linear predictive coding, it can actually be dated back to the 1920s.
That's
So the work
certainly
of
true.
Buell, for
Right,
example.
that's certainly true. And in fact, the whole business of linear difference equations probably goes back 400 years. And you know, people have documented that a little bit too. But I guess what happened at this moment in history, the technology merged with the ideas. There's another anecdote. A friend of mine visited Bell Labs, I think about 1948, because he was interested in the information theory. Shannon had just done information theory. And he sat around at a lunch table with Shannon and Bode and a few other guys, and they were talking about how to do digital filtering. I mean, they weren't going to do it. 1948 was too soon. But, I mean, the concept that you could do it on a computer, in other words. There was a ways to do it digitally. So this whole set of concepts, nobody came along and said, I suddenly had a brainstorm. We can do it on a computer. You know, it was around, like nearly everything. Yeah.
So one lesson to learn from this is to watch out what other fields are doing, right?
I think that's really a great idea. I think you should. We all try. I try very hard to do that. I don't succeed very well all the time because there's just so much going on. Yeah. But I agree completely.
So as a reward for all those of you who stayed so long on a Friday late afternoon, there is a courtesy of local chapter IEEE, a little refreshments, and I believe that Professor Foley knows where it is. I think it's next door, right?
It's in the kitchen area.
So
go out and slightly to the left and around the corner.
please stay around, and I hope that...